Welcome. In this lecture, we'll discuss atmospheric pressure, Boyle's law, and Bernoulli's principle. As a reminder, the four states of matter that we are dealing with are solid, liquid, gas, and plasma, and I should say we're only really dealing with the first three. And as a quick reminder, plasma, though we won't be talking about it in this course very deeply, it is the most common phase in the universe, since Sun and other stars, as well as much of the intergalactic matter, are in the plasma phase. To go from solid to liquid to gas to plasma, you must simply add more energy to the system. Today we will be talking about gases. Some qualities or characteristics of gases is that they have a non-constant shape and a non-constant volume. And again, as another reminder, all three of these are considered fluids. And fluids, as we defined previously, are a collection of molecules randomly arranged and held together by weak cohesive forces and by forces exerted by the walls of a container, if contained. In other words, a substance that deforms continuously when acted on by a shearing stress of any kind. Liquids and gases and plasmas, as we said in the previous slide, are fluids. And as we touched on before, fluid mechanics is split up into two categories: fluid statics, which is the study of incompressible fluids at rest, in other words, stable equilibrium, and fluid dynamics, the study of fluids in motion. Today we will continue our discussion on fluid statics as we address atmospheric pressure and Boyle's law. Then we will talk briefly about fluid dynamics through a brief introduction to Bernoulli's principle. Atmospheric pressure. Just as water pressure is caused by the weight of water, atmospheric pressure is caused by the weight of air. Other properties of atmospheric pressure is that it varies from location to location because of the differing densities. Therefore, it is not uniform from one location to another, and measurements are used to predict weather conditions. Weather can be predicted by taking measurements of atmospheric pressure. Consider a vacuum pump. There is pressure in both locations. If the pressures on both sides are equal, then equal and opposite forces are produced. But what happens if the atmosphere within the tank is pumped away? Well, now the pressure on the inside is no longer there. So the force produced by the pressure on the inside is zero. So we only have the force on the outside. So what if we add a weight to this piston? Well, what we see is that the force due to the atmospheric pressure is countering the force due to the weight of the block. So due to this vacuum, atmospheric pressure creates force that can hold the weight. And just as with water, as was already mentioned, pressure exerted against bodies immersed in the atmosphere result from the weight of air pressing from above. At sea level, the weight of air per square meter is about 100,000 newtons. So the atmospheric pressure is about 100,000 newtons per meter squared. This air pressure, due to a 30-kilometer column of air, is equivalent roughly to a 10.3 meter column of water. In this picture, the atmosphere pushes water from below up into the pipe that is partially evacuated of air by the pumping action. If a perfect vacuum were created by the pump, the deepest well could be no more than 10.3 meters deep if water is to be pumped up. Let's take a look at this. You cannot drink soda through the straw unless the atmosphere exerts a pressure on the surrounding liquid. So strictly speaking, the girl does not suck the liquid up the straw. She instead reduces the pressure in the straw and allows the weight of the atmosphere to push the liquid into the straw and then into her mouth. What if the glass that she's holding is corked? The atmosphere that is in the glass cannot be refilled by the outside air. When the girl drinks some of the liquid level lowers, causing the limited amount of gas above the liquid to expand to fill the space. Since the gas has expanded within that glass bottle, the gas is less dense. As we know from our pressure equation, pressure depends on density. Lowering the density lowers the pressure. Therefore, as she drinks more liquid, the pressure that presses the liquid up into the straw grows weaker and weaker until it's no longer strong enough to push the liquid up the straw. The first barometer was created by Evangelista Torricelli. He took a mercury-filled tube, tipped it upside down, mouth downward, in a dish of mercury. The mercury within the tube dropped to a level at which the weight of the mercury in the tube was balanced by the atmospheric force exerted on the reservoir. And remember Pascal's principle that pressure is transmitted undiminished. So if the atmospheric pressure increases, the tube's level will increase. So that level of mercury will rise. If the atmospheric pressure decreases, the height of the mercury column will decrease. So this became a way of gauging the atmospheric pressure. We just look at how high in the tube the mercury is, and that will tell us how strong the pressure is outside. At standard pressure at sea level, the height of the column of mercury is 760 millimeters. Or 76 centimeters. Problem 1. What holds the water in the straw? The atmospheric force, which is upward, balances the weight of the water, which is downward. I'm sure you've tried this when you've gone to a restaurant. You have a straw in your drink, and when you're just bored or messing around, you put your finger at the top of the straw and pull the straw out. And you'll notice that there will be some amount of liquid that is able to be held inside the straw. Now there's a limit to how much liquid can be in the straw, and that limit is set by the atmospheric pressure that produces the atmospheric force. So the weight of the liquid in the straw must be equal to the atmospheric force. If the weight of the liquid in the straw is greater than the atmospheric force, then some of the liquid will drop out until what remains is enough liquid that weighs an amount equal to the atmospheric force applied to that liquid. Boyle's law. Consider a piston with a set number of gas molecules inside of it, which occupy a certain volume, which we will denote here as V1. The pressure gauge reads some value, which we will denote as P1. What happens if the volume is decreased? Well, then we have a new volume that is smaller, and we have a different higher pressure, P2. We can compare the two scenarios here, and this leads to something known as, well, Boyle's law. Assuming that the temperature of these two pistons, of the gases inside these two pistons, remains the same, then we get Boyle's law, where the product of the pressure and volume in the initial scenario is equal to the product of the pressure and volume in the final scenario. And again, this is contingent upon the temperature being the same between these two scenarios. Let's discuss Bernoulli's principle. So consider a continuous flow of water in a stream, or in this case, perhaps in a pipe. Because water doesn't bunch up, the amount of water flowing through any given section of pipe must be exactly the same as the amount of water flowing through any other section of pipe. And we're denoting these sections by specific areas, where the first section is considered area 1 or A1, and the second section is denoted as A2. So that is, the amount of mass passing through one area of pipe must equal the amount of mass passing through another area of pipe. This is known as the principle of continuity. Mass must be conserved. And how is this achieved? Well, the velocity of the fluid through the larger area is smaller than the velocity of the fluid through the smaller area. So again, velocity of the fluid through the large area is small, but the velocity of the fluid through the small area is large. And for an incompressible fluid, we can write a simple relationship. We say that A1V1 equals A2V2. So the product of the area with speed is known as the volume flux. So we say that the volume flux through one area of pipe equals the volume flux through another area of pipe. So this can also be called the flow rate. And again, it is derived from the continuity principle. I didn't really show the derivation here, but it can be shown very easily. But we still haven't gotten to Bernoulli's principle, so let's get to it now. Bernoulli's principle, where the speed of the fluid increases, the internal pressure of the fluid decreases. So Bernoulli's principle, for simplicity here, is stated without proof, though it can be easily derived using the work-energy theorem discussed in an earlier chapter. Consider some bubbles in the larger area of the pipe, or the larger part of the pipe. What happens when they go into the smaller part of the pipe where the fluid speed increases, which we saw in the previous slide? We know that the fluid in the larger area of the pipe goes slower than the fluid in the smaller area of the pipe. So what happens to the bubbles as they move from this larger area into the smaller area of pipe? They increase in size. Why? Because the pressure in this smaller area of pipe decreases. So the bubbles get larger. So the pressure on the left part of the pipe is greater than the pressure on the right part of the pipe. And this is Bernoulli's principle, that where the speed of the fluid increases, which we know that the speed is greater in the smaller area, then the internal pressure of the fluid decreases. And we can see this by the size of the bubbles. The bubbles get larger, again, because the pressure on them is less. Another application of Bernoulli's principle is a wing. And here we're looking at a two-dimensional wing, also known as an airfoil, where you see that the air pressure above the wing is less than the pressure below the wing, which causes a net upward force that we would call lift. And this is what elevates planes into the air. This is the upward force, and that's why these wings or these airfoils are shaped the way that they are, is to produce this lift due to a difference in pressure between the upper and lower surfaces. Another example is the wind over your home. In high winds, air pressure above a roof can drastically decrease, resulting in roofs being ripped from homes. Because if the speed of the air is very fast over your roof, but the speed inside your home is very low, that means you have higher pressure inside the house than you do outside the house. And so the net direction of the force would be from the inside of the house to the outside of the house, which would push the roof off. And this is what often happens in tornadoes. Another example is, well, a baseball. When the baseball isn't spinning, the airspeed above and below the baseball are the same. When the baseball is spinning, the airspeed above and below can be different, producing a different pressure and therefore applying a force on the ball to make the ball curve. Similarly, if we put two boats in a bathtub, or it could be out in the ocean too, but this is an easier one to show, and I put a hose that increases the speed of the fluid flow between the boats, that will decrease the pressure between the boats, such that the pressure on the other sides of the boats, outside the boats, will press the boats toward one another. It draws the boats together. So in summary, we have discussed atmospheric pressure, Boyle's law, and Bernoulli's principle. I'll see you next time.